So this is the time for our annual Connelly lecture. This lecture series in informatics leadership is to acknowledge the work of Dr. Donald Connelly in pathology informatics and the body of work that he and his colleagues created. From 1975 forward, Dr. Connelly was professor of laboratory medicine and pathology at the University of Minnesota Medical Center, was the director of Health Informatics Division, co-director of the training program, and he assumed several responsibilities in our university. He and his colleagues developed the first successful UMN laboratory informatics system. They used their own computers. There was no cloud back then, and they developed it and deployed it, and it was very successful. Dr. Connelly assumed several educational and research positions at the University of Minnesota. His research focused on clinical decision-making related to effective laboratory testing and the development of informatics technology tools clinicians choose to use to support their clinical practice and decisions. Dr. Connelly was the fellow of the American College of Medical Informatics, a founding member of the Medical Informatics Association, and was awarded the second Lifetime Achievement Award from the Association of Pathology Informatics in 2003. We are honored today to have members of Dr. Connelly's family with us. And this lectureship is possible through the generous sponsorship of Mike and Wendy Loge. So thank you very much for that. We all know Mike has, before coming to the University of Minnesota, he spent 10 years of his career at the University of Michigan in pathology informatics. He worked with Dr. Bruce Friedman. Even though Mike's PhD and official training was in psychology, but he chose to work in informatics, and he was very instrumental helping us with various educational tools that we use in our department. Wendy is the former Dean of Libraries in the University of Minnesota. She served in that role for about 20 years, and she is retired now, and I understand Wendy and Mike are focusing their time to enjoy their grandson, so congratulations for that. Following the lecture, we have the reception outside, and you are all invited. This reception is sponsored by the Connelly Lectureship and also sponsored by the Department of Laboratory Medicine and Pathology to celebrate the 50th anniversary of the ETBell. Our speaker today is Dr. James Harrison, and he will talk to us about the perspectives of laboratory test validation in the artificial intelligence era. Dr. Harrison is a professor of pathology and the director of clinical laboratory informatics at the University of Virginia, where he also co-chaired the Laboratory Stewardship Committee. He has over 35 years of experience in clinical and research informatics, and he is active in residency and training and fellowship training and clinical analytics, including machine learning and software development. Dr. Harrison is the PI on several prestigious grants, and he assumed several administrative and educational roles, all related to informatics. His role in CAP obviously was very instrumental in the area of artificial intelligence. Jim was also a friend and a dear admirer of Dr. Donald Connelly. Jim? Dr. Harrison, I will gift you a copy of our University of Minnesota book summarizing 50 years of informatics, and I hope you add this to your library. It has very good information and very interesting pictures inside. It shows how. As you all have seen this probably before, this is the plaque that lists all our guest speakers for the Connelly lecture. And Dr. Harrison's name appears here. This plaque is hanging in our department on the 4th floor. Dr. Harrison.
Oh, well, thank you very much. As was noted, I counted Don as a friend, and I served for many years on CAP committees and in the Association for Pathology Informatics. With him, we had an opportunity to work together. I enjoyed that very much, and also enjoyed just the opportunity to compare notes and talk about our interests. Over the years, I really appreciated and valued his quiet encouragement, I guess, of my career, and I'm really happy to have this opportunity to honor him. All right, so I don't have any conflicts to report. I am vice chair of the College of American Pathologists Artificial Intelligence Committee, and I also am past chair of the Informatics Committee. And I'd like to echo Dr. Nolan's comments about the opportunities that these committees offer to junior members. A couple of years ago, the CAP increased the number of junior members per committee from 1 to 2, so there are more opportunities now to serve. And this is a great way to get to know pathologists in an area of interest to you, a range of seniority. And there's plenty of things that junior residents do to contribute to committees, and if you can find the time to participate, I'm sure you'll enjoy it and learn a lot. So I encourage that. All right, so we're in exciting times with artificial intelligence. Revolutionizing healthcare from this year. Redefining speed in clinical decision-making. Revolutionizing healthcare with AI, a new era of efficiency. Radiologist level classification. Well, that's okay, it's radiologists. Pathologist level classification of histologic patterns, pathologist level interpretable whole slide cancer diagnosis, and FDA backs clinician-free AI imaging diagnostic tools. So maybe there's a potential for disruption there somewhere. But also inconsistent performance, reproducibility, still a ways to go. Stress testing reveals gaps in clinical readiness. Black boxes. Gender imbalance causes bias. More bias. Should we be afraid of medical AI? And how catastrophic is it if the bubble bursts? Well, what are we going to do about this? How will this affect pathologists? Well, wait a minute. Okay, that's where I thought it. All right, so the expectations are, of course, with the caveat that whole slide imaging is a prerequisite. There are going to be a bunch of really interesting tools available to us. And I'm not going to go through, in detail what the tools are, but they're going to relate to case and slide management, finding, marking, and quantitating features on digital images, aggregating and summarizing data, getting the data that you need, where and when you need it, fluid dictation and voice command, so Star Trek-like interacting with computers, and screening interpretations, so preliminary interpretations rapidly rendered in AP and CP. Also, improved quality control, auto verification, multi-result delta checks, sample swap detection that's improved over what we have today. Things related to lab utilization and decision support, potentially real-time identification of high and low-value tests based on the patient context, and predictions of diagnosis, prognosis, clinical course, and response to therapy, so more value out of data that we have now. Well, the CAP thinks we're going to be in charge of this. So this is just some excerpts from their AI policy from a couple of years ago. Expansion of pathologists' responsibilities to include AI will constitute an important new element of pathologists' role as CLIA lab directors. The CAP supports and encourages the professional and critical role of pathologists in development, implementation, and maintenance of these systems. Pathologists' engagement in these systems allows the capture of pathologists' unique knowledge into them that will improve them. And pathologists must have a leadership role in selection, configuration, et cetera, of AI systems involved in pre-analytical, analytical, and post-analytical phases of laboratory workflow. So we're going to be in charge, all right? Well, what resources are there to help us with that? Or what are the guidelines? What's the regulatory environment? Well, let's check the FDA. In September, the FDA issued a request for public comment, measuring and evaluating artificial intelligence-enabled medical devices in the real world. That comment period is open now, closes December 1st. Questions that they're asking are, what metrics and performance indicators do you use to measure the safety, effectiveness, and reliability of AI-enabled medical devices? What tools, methodologies, or processes are you currently using to proactively monitor AI-enabled medical device performance? So the FDA is asking us how we're doing this and sort of trying to figure this out. That's going on currently. There are other things that are similar. ISO has a document that they're working on, Part 1, General Principles for the Application of Artificial Intelligence in the Medical Laboratories. Comments were requested on this last March. The document was in extreme early draft form. So a lot of work still to be done on that. There is a industry government academic consortium called Coalition for Health AI, or CHAI, that was put together about maybe 2 years ago now. They have something they're working on called a Responsible AI Guide for Healthcare Applications. Now, this is not lab specific, it's just healthcare in general. It's also a draft. The last version they have is from 2004, but that's not version 1. So it's still in draft form, but you can get it and read it. It does focus on the AI life cycle and sort of standardized AI performance information, and they are working on some things that I'll talk about a little bit further on in the talk, but this is early. Paragon Institute is a healthcare think tank. They released a document in September about managing AI performance evaluation through targeted post-market surveillance. So the idea of setting up a public-private registry for AI surveillance with problem and outcome reporting, like is done in other situations. And this would be under the FDA's auspices, built on some of the FDA surveillance activities for other devices. That report is downloadable at the address there. It's been proposed that there should be an extension of CLIA to cover AI that would license local AI operations units. It would use existing accrediting agencies, and there would be competency requirements and some validation verification requirements and performance monitoring requirements that are analogous to what's in CLIA now. And this would be more broadly applicable outside of laboratories. And then there are some CAP checklist items related to AI performance verification and monitoring that are currently in draft form. The CAP is not going to release a new checklist next year, so these would potentially get into the checklist in 2027. So all of that's developing. So right now, we don't really have a lot of established best practices and guidelines to help us out with managing these tools. There's some other issues that we need to think about in the laboratory too. Most labs are going to install pre-developed AI models. Now, that's not to say that laboratories won't be able to develop their own AI models. Some laboratories will, and you've heard mentions of things like that. But most laboratories across the country, by and large, will be installing AI models that are developed elsewhere. There's an analogy there between commercial tests that are FDA approved and laboratory developed tests. And there are likely to be differences in the requirements that are also analogous. We should make a distinction between embedded systems and AI models that are that work on data that is developed or created locally by systems not under the control of the AI. So a lot of radiologist systems are built into the radiology instruments, and they're working in an environment that's the same from one place to another because they're completely inside the instrument, and all the input data to them comes from the instrument itself. We have some things that are somewhat similar to that in blood smear analysis, urine sediment analysis. There are neural networks in some of those instruments for the identification of the elements, but those reagents come from the manufacturer, and those are essentially operating completely within the instrument, and their environment is pretty much the same from location to location. And so for those, it's probably reasonable to regard them as part of the instrument. And so you do the instrument validation as a whole rather than separate out the AI from it. On the other hand, AI that receives data from a variety of different points in the environment, which may differ from site to site, potentially should be handled differently, and we'll talk about that. So how is CLIA applicable? Well, if the output of an AI yields or contributes to a laboratory result for a patient, we should and it's done in the laboratory, we probably should default to treating it like or applying CLIA requirements to it as much as we can. That would require formal validation. It would require a QC plan, probably an individualized quality control plan, IQCP, and performance monitoring. CLIA is not applicable outside of the lab, so the radiologists don't have to do CLIA stuff with theirs. Theoretically, something like a sepsis prediction algorithm could be implemented by the IT department in the EMR and not be subject to any of the CLIA requirements, even though it uses lab test results to make the prediction, and the prediction is used kind of like a result. In fact, that happened, and it turned out that the models were not verified and they were wrong, or in many places they were very suboptimal, say it that way. But inside the laboratory, because it's the laboratory and because CLIA applies to the lab, we need to take CLIA into account. All right. So I talked about AI hype, expectations, available management guidelines, which really aren't there. But what I'd like to talk about for the rest of the time is issues related to machine learning performance, generalizability, bias, stability, and then performance assessment, particularly for AI classifier systems. Classification systems are going to be an important component of these AI systems. And then performance verification and performance monitoring of machine learning systems, what that might look like, and some examples of both of those. Okay, so before jumping in, just a little bit of background. So AI is a broad area. It includes, basically general or strong AI, which is still a research area. That's an AI that basically is capable of the kind of thinking that humans do. And narrow AI, which is focused on particular tasks. And that's what we have now. Narrow AI includes expert systems, which are based on human curated knowledge bases. We've had those for some time. One of the challenges with them is that creating and maintaining the knowledge bases is really effort intensive. And then what's causing all the excitement now is machine learning, which doesn't require a curated knowledge base. You can just feed it lots of data and it finds the patterns in the data directly from the data itself. Now, there are a variety of different kinds of machine learning algorithms, and some are listed there. I'm not going to go through those, but I'm going to focus on classification, which can be binary, that is positive or negative answer, or multi-class classifiers, which is a classifier that can yield more than 2 answers. If you're interested in more information on this, there is an introduction to artificial intelligence for pathology that was published a few years back in 2021 by a group of us from the CAP. All right, so in simple terms, a machine learning an algorithm is a recipe for a model. And I just want to point this out because I'm going to talk about machine learning models. And so what do we mean by a model? Well, to make a machine learning model, you start with real operational data. It can't be idealized data. It has to be data like what the model will see when the model is operating in the real world. So real data, normalize it, label it, clean it up a bit so that it doesn't have missing data and that sort of thing. And then you take a machine learning algorithm, which again is the recipe, and then train it to create a model. And an analogy to the algorithm might be something like just a linear equation, where if you're given X, you want to calculate Y. In the algorithm, that's basically the structure of it, the form of it, and the steps you take. But the parameters, M and B, are empty. So you actually can't use it to calculate a real value. Now, this is so simple that we can actually use math, calculus, to do an optimization on this. And given a bunch of data, we can calculate what M and B is. For the analogy to machine learning, you would take M and B and put random numbers in there. And then you would have a bunch of data that was more or less linear, and you would start comparing the result you got to the result that was in the data. And if the answer is wrong, which it definitely would be initially, you tweak M and B a little bit to make it a little bit more right. And you do that a few thousand times. And over time, those values converge on the values that you would have gotten if you had done a linear regression on this. So it's sort of brute force, and ultimately you get values there for the parameters, and that is a model. It's a parameterized algorithm. So when I talk about a model, that's what I'm going to be talking about. So let's look at something a little bit more complicated. This is a diagram of a deep neural network. It's deep because it has more than one hidden layer between the input and the output. In this neural network, which is actually a diagram of a real one, there were 128 nodes in the first layer under the inputs, which I've got, I'm not showing all of those because it really is a pain to draw these little lines. So ... 56 nodes in the next one, 16 nodes in the next one, and then 1 node in the output. So those are the hidden layers. And then there are 4 input features. So this is small, even though it was real. Now, if we look at the nodes, each node you can think of as having a little equation in it. And the equation takes the inputs, which are the features, the input data, and each feature has a coefficient in front of it. And then there's an overall number that's added or subtracted from the value of the node. And then the value from calculating that comes out the bottom. Now, I'm not trying to say that this is the equation. It's just an illustration. But the equations aren't that complicated. And so each node produces a value, and and those flow down through, and then the bottom node is a little bit different because it either assembles the values and presents them as a probability of one of the classes in a binary classifier, generally a probability of the positive, or it applies a cutoff and presents it as positive or negative by comparing the value to the cutoff. Now, the coefficients of the parameters, the coefficients of the input data are the weights, and that value that's by itself that gets added or subtracted at the end is the bias. And the weights and biases together are parameters, and each node has parameters like that. So there are lots of parameters here. Now, in a real neural network, there are really lots of parameters for networks like, ChatGPT. Those are proprietary, so we really don't know exactly how many parameters they have, but rumor has it is that there's more than 1 trillion. There is a lot of parameters, which makes these potentially complex, and I'll show you why. But when this is trained, initially, all of those values, all the parameters are set to random values. And then as you train over and over and over again, they are slowly tweaked toward values that make the output more and more correct. And by, coloring the values, what happens is the nodes become able to amplify certain patterns of the inputs or suppress them. And so some patterns of value disappear, others persist on through to the end, and they increase or decrease depending on the nodes. And you can have trillions of patterns through this system. Now, when we do, say, immunoassays or chemical assays, the results of those are based on a mass action. So millions of molecules all behaving the same way. And if we add some, we get more of a signal. If we subtract some, we get less of a signal, depending on, the kind of assay it is. In this, and so there are physical, there's a physical basis for what we're seeing. In this, all of those parameters are put just by tweaking. And so there's no physical relationship between the parameters. And so the output doesn't have to be smooth. It can be discontinuous. Slight changes in the input, slight differences in that pattern can yield huge differences in the output or not, depending on how the pattern of parameters all through the neural network are laid out. That's one reason why they talk about these things as black boxes. It really, for big ones, it becomes not practical to try to calculate and visualize what's happening. Okay, so I said those things. And so the imprecision doesn't follow a defined pattern, and where you might have imprecision that's, typically from physical processes, it's a Gaussian or normal distribution. Here it's, you don't know what the distribution is. So how do you measure the performance of these? Well, for classifiers, you're typically interested in discrimination or calibration, or discrimination and calibration. The metrics are basically a typical confusion matrix, and they're generally familiar. Accuracy, sensitivity, which is called recall in AI and information retrieval. Specificity, positive predictive value, which is also called precision in AI, negative predictive value in others. And then, as you're familiar, often used in laboratory medicine, ROC curves express the overall operation of the test by plotting the true positive rate or sensitivity on the y-axis versus the false positive rate on the x-axis. And what you want is something that has a high true positive rate at a low false positive rate. So that pushes the curve up into the upper left. So A is a better model, or is a better test or model if it's AI than B, because it has a higher area above the diagonal line and it's more in the upper left. There are also other metrics like the F-score, which balances precision and recall, and there's several different F-scores that balance more one way than the other. And then there's a similar metric called Matthews correlation coefficient that's useful for comparing classifiers that particularly work with rare cases, that is, imbalanced cases, where you've got almost all of one thing, but a little bit of the other thing, and you really want to find that. For digital pathology, when you're looking at detection of features on glass, on whole slide images, free response receiver operating characteristic curves or FROC curves are often used, which plot the sensitivity on the y-axis versus the mean number of false positives per whole slide image on the x-axis. You want something that will call the slide correctly. You want it sensitive, but without a whole lot of false positives. And so that allows for more than one false positive per slide. The issue with a slide is there are lots of different points that you might be able to call, and you want it to call them, as many of them as possible, correct. The other metric or the other area that classifiers are evaluated in is particularly when they return a probability of a class, like how probable is this particular positive, 20% probability, 80% probability, or what? And here you plot the probability that you call, which is the expected probability, with what the outcome turned out to be, which is the observed probability. And what you want is for those to match up as closely as possible. So the dotted line. The orange line shows a classifier that's pretty good. It's off a little bit, but it pretty much follows the line there. The blue line is a classifier that at low probabilities, it overpredicts, and at high probabilities, it underpredicts somewhat. So that would have, you would have an issue here when you were calling low probabilities. You would be missing those. Even though you were at the higher probabilities, you would be more or less okay. You can also, if you have deviations here, you can test whether the deviations are significant or not using the Hosmer-Lemeshow test, which compares the probability that deviations are different from the line of identity in the middle. So if you have a small p, that's a high probability that there really is a difference. And you don't want there to be a difference. If there's no difference, then that's good calibration. So a large p is good calibration. So discrimination and calibration. All right, so to develop a model, you start with data like we showed, normalize it, label it, split it into training and test data, and then take your model, take your algorithm, and I'm using, just a little representation of the neural net we showed, and train the use the training data to train the model to create a parameterized model. Then you test that with the held out test data that the model hasn't seen, and that's where your performance metrics come from that. And if it performs well, it's a validated model for that location and for that data. So you can actually apply this to data that's equivalent to the data you started with. But when you want to take that model and put it at another site, the question is the data at that site comparable to the data that the model was trained on? If it's not, the model might have poor performance. So you can't assume that. You need to check it. If you test at the deployment site and it works well, you can call it, that is referred to as external validation. The fact that you've externally validated at one site doesn't mean you don't need to test at other sites, because you still have the issue that another site might have different data. But you have validated for that site. And so at least with respect to that one additional site, you do have generalizability. So the ability of the model to work across multiple sites means that it has at least a certain amount of generalizability. Now, if it doesn't match, there's still, depending on the kind of model it is, the possibility that you could tune the model for the site and improve its performance and actually make it acceptable. And that's referred to as transfer learning. So you can train a little bit more with data from that site. And if that's done correctly, and if the model will accept it, then you may be able to recover the use of that model. Now, once that's done, it's not the same model as the first model. It's a different model, but it has been set up so it is capable of working at the second site. All right. So let's talk a little bit about, so the question there is, then is where does the variation between sites come from? There are traditional pre-analytic variables listed there, and the pre-analytic variables can vary site to site. There are also site differences, different processes and materials, different test methods and instruments, patient population and subgroup differences. So that's where where the differences between sites come from. Now, is that an issue in pathology? And it turns out there are a lot of pre-analytic variables in histology that will make things look different, and that affects, or at least potentially could affect, the performance of a model working against those images. So does it really? Well, looking at a number of sites across the top, the color and grayscale characteristics of images from those sites does differ. Is this enough to affect machine learning? Well, before I get to that, and there are a number of image artifacts, ones that we're familiar with, that do affect machine learning. And so different types and incidents of artifacts could also be site differences that affect the performance of a model. So then the question is, well, does it really do that? And in general, yes. So this is an example of data or a model that's trained on local data on the left and tested against local data or data from multiple sites that was part of a machine learning contest about breast cancer. And so when tested on local data, the ROC curve is near the upper left, pretty good. Chameleon data, it's not horrible, but it's lower. If you train it on the chameleon data, which came from a variety of sites, the performance is pretty good on the chameleon data, as you would expect, but the performance is really low on the local data. So depending on how you train a model or what the model is trained against, it may or may not perform well against histologic data coming from other sites. There's a lot of work on normalizing histology, but it's not a problem that's been completely solved yet. That means that transferring models from one site to another or implementing a commercial model at a site will have some, well, you definitely need to test it, and there may be some issues related to generalizability. I'm going to skip over, I'll mention a couple of things, but I'm going to skip along a bit on the other problems. Embedded bias is bias that's trained in. It's in the training data. Drift and shift is bias that develops over time because the input data changes. And so the input data becomes different from the training data. Here are some examples of embedded bias in healthcare. The EPIC sepsis prediction model is there, but there are also a number of others. And we've seen this kind of problem with outside of healthcare and within healthcare. It's a fairly common thing. So it's something that we need to be on guard against. I mentioned that bias can develop over time. It can develop relatively quickly, which is data shift. It can develop slowly, which is data drift. Data shift and drift can actually take several forms. If the distribution, the statistical distribution of features changes, that's referred to as covariate shift. Sometimes it's called concept shift too, but concept shift really ideally refers to a situation where the meaning of a feature changes. So the concept that value stands for changes, and that does happen in medicine. So there are a couple of ways that drifts and shifts can occur. Actually, let me see. There we go. Oh, and I should say, drifts and shifts are expected. in a dynamic environment like healthcare. And this is just an example of ICU length of stay prediction from a model trained from data from 2001 to 2002. And over the next 12 years, it progressively declined. If you go and train on any one of these intermediate years, the model performance will jump back up to 90%, but then start declining after that. And that's because processes, tests, the test vendor, things like that change over time, and that makes the data change and deviate from the training data. So it's important. Performance monitoring turns out to be important. And then there is the potential for instability. This is an adversarial attack where you can search and find random data patterns that if you add them to an image, it will basically break the model. And so the top image is a benign mole. This works for pathology images too, but the illustration is dermatology, which was called benign with 89% probability or 90%. And then when just a light bit of that noise was added, which you can't really see, it became over 99% probability of malignant. The same with the one at the bottom, only reversed, 97% malignant, add the noise, now 75% benign. Now, you have to search for these patterns. But what this is telling you is that the response of the model is not continuous over every possible pattern. There are gaps in there, and when it hits one of those gaps, you don't really know what the response is going to be. And so it's important that testing determine that, these aren't a substantial problem. Okay, so we need to be able to meet and maintain established clinically acceptable benchmarks for these AI models, just like for regular lab tests. And there is potential for harm and inequity. And so it's, besides being a technical requirement, it's an ethical requirement. Now, this is just an overview of the typical analytical verification from a high level. This is for example, for an FDA-approved test, you need to verify accuracy, precision, reportable range, demonstrate linearity, verify the reference interval, and then follow the recommendations for QC and proficiency testing. There are some differences with machine learning that where machine learning methods have some analogies, but they also have some differences. The verification methods aren't standardized the way they are for regular lab tests. The regulations may differ, as we said, depending on where the test is implemented, in the lab or outside, being subject to CLIA. There is sensitivity to subtle data characteristics and patterns, and we showed an example of that, or a couple of examples actually. The need for site tuning, that is, transfer learning where the model becomes different, means that external challenge tests like proficiency testing aren't useful, because you can't take a specimen or an image from somewhere else, send it to a site, test it, and have that image represent the ability of that model to make correct decisions about that model's own site's images. And the models differ one from another across sites. There's a potential for subtle biases in the data and group-specific biases. We mentioned the unexpected brittle responses. And when you're dealing with a classifier, there's no reference range. The output tells you what it is. So in fact, the reference range is actually incorporated into the result. All right. There's also not a standard way to express the performance of these models, but there is a proposal for creating essentially package inserts with the models that have a standard form. And this has been discussed for a few years. These are sometimes referred to as model cards, and this is an early example of one where it had the details of the model, the intended use, factors that affect the model, the metrics that are used to define the performance of the model, the actual data, the performance itself using those metrics, and then descriptions of the training and testing data. And this would allow you to compare this model to the characteristics of another model and to compare this model to its performance or compare its benchmark performance to its performance at a particular site. So we talked about the traditional verification testing. CLSI, as you're aware, provides these standard optimized strategies for this. Machine learning classifier performance, we don't have CLSI methods for that yet, although eventually I expect those will be there. But the performance has a different context and performance profile, as we've discussed, so you can't just apply CLSI methods directly. The sample number calculations for doing comparisons are typically those have been carried out with standard power calculations. And so there is a recommendation from by a group that included Matthew Hanna from Pitt and also Jensen Seeholt from Mayo to basically do a power calculation which with the equation shown there using one-tailed z-scores to determine how many samples you would need to see in a classifier to detect a drop in accuracy from 95 to 90%. So the example is that the claimed accuracy is 95%. You're trying it at your site. You want to be able to detect if the accuracy is 90% or lower, so a 5% or more drop. So if you run the calculation where the z-scores are in the z's, of course, and P0 is the probability that your the claimed performance, 0.95, and P1 is the performance that you want to be able to see that or below. You can run that through, and you get that for 95% confidence and 80% power, you need 150 samples, 75 positives and 75 negatives. Now, if you want to verify the sensitivity and specificity, that takes more. But in general, for a verification at a site, you would, or rather a verification of accuracy, you probably wouldn't recalculate the sensitivity and specificity at your site. You would check the accuracy. And so to limit the number of specimens, that could develop into a standard approach. And then Olson and co-workers just this year published numbers recommended for testing AI assistive tools in AP and recommended that 2 observers be used, each with at least 189 cases with and without the AI assist. So 189 cases with the assist, a washout period, 189 without, or vice versa. And then do that with each of 2 observers. Now, this is more than the CLSI recommendations for just bringing in an FDA-approved lab test. But remember that with a classifier, you're essentially testing the classifier itself and you're testing the reference range sort of all at once, because the classification takes into account the internal cutoff. And a reference range is basically built as a 95% confidence interval on the normals. Here, you're looking at an optimized cutoff between 2 classes, which could be normal and a particular disease state. And so that's a more sort of precise location of the cutoff and potentially requires more cases to be able to validate it, or a higher sample number. For repeatability, the goal is to match the claimed proportion of correct results from a single specimen, ideally over multiple days. So you should be able to, if a specimen is positive, it should stay positive, at least within a certain rate, and negative should stay negative. And the recommendation here is to have 10 positive and 10 negative specimens with 6 replicates of each. So you have 60 results for each class, 60 positives, 60 negatives, and just 10 specimens of each with 6 replicates of each of those, and probably matching the way that the manufacturer did it, because that's what you're comparing to. But ideally, that would be done over at least several days. So you get between day as well as within day repeatability. And then that's a screening study. If it fails, there's still a possibility of doing a bit more detailed precision study, which might still be acceptable and let you rescue the model. Okay, for calibration verification, that's, again, remember, checking the probability predictions. You need cases with known outcomes. So this is going to typically be done on retrospective data. And you'll typically bin that into low, medium, and high predicted probability, maybe is ideally 3 to 5 bins. So actually a lot like a linearity study. And then calculate the average outcome proportions in each bin, and rather, the average predicted probability in each bin should match the average outcome in each bin. And to test those, you can use the Hosmer-Lemeshow test that we talked about before. Now, if calibration fails, there is a possibility for mathematically correcting it, or for retraining a system. But your ability to retrain effectively depends on how much data you have. And on the left, this is a simulation showing calibration. Let's see, the dotted line that's in the bottom is uncorrected. That's when calibration is off. And then you can either mathematically correct or retrain and get good results if you have a lot of data. If you don't have much data, if you try to retrain with less than an optimal amount of data, you can basically destroy the model's performance. And so it's actually better in that case to do the mathematical correction. And some other work has extended this to, if you initially have a discrimination error, you may also be able to mathematically correct that to an adequate point. And so we may see this become part of the standards if models are built this way, so that you can tune the model mathematically without having to retrain it, at least to operate for a while. So if you're doing, performance evaluation and your model declines in performance, you may be able to tune it back up to keep going until you come to the point where you would need to retrain. Or if the manufacturer is aware of it, they would retrain and give you a new model. Okay, so let's look at a couple of examples. The first one is site verification for AP. There was a commercial AI model for diagnosis of prostate needle biopsies. This was going to be deployed as a routine second read system. This was at University of Pittsburgh. And the model was tuned to the site using 159 local case parts, so transfer learning. I actually talked to Laron Panowitz, and I wanted to know what the performance prior to tuning was. The tuning was done by the model vendor, and he didn't have that data, which I was disappointed in. I would have liked to have seen, what the generalizability was initially and how much improvement they got with the tuning. However, they did a power calculation to define the sample size for verification, and they used 100 cases with 379 parts and a total of 1,600 and a few more slides. The gold standard was the initial pathology report. They took a sample of that and reviewed it with blinded pathologists to confirm it. And any discrepancies were resolved by a third pathologist. So that was their gold standard. their cancer incidence was a bit higher than the benchmark cancer incidence data set. The area under the ROC curve, which isn't sensitive to differences in incidence, was comparable. This is after tuning. The sensitivity was comparable. The specificity was a little bit higher at the site. The positive predictive value was a good bit higher, but that's probably related to the higher incidence of cancer in the test set at the site. And negative predictive value was about the same. And so this was taken as evidence that the model was appropriately valid, or that the model was functional and operating similarly to the benchmarks and was appropriate for use. Now, for performance monitoring, the goal is to confirm and document that the model performance is stable, or to detect a defect in the system or data drift or shift, and then to take appropriate corrective action if it's needed, and also periodically to report the performance and any problems that have been encountered to the developer of the system and to the FDA. There are three strategies to this. To performance monitoring. One is to evaluate the input data stability. So this can be a flag to possibilities of model performance problems, because as you remember, models can be very sensitive to the patterns in the input data. And so there are ways to evaluate the distributions of the input features, like population stability index, Kullback-Leibler divergence, or chi-square goodness of fit, or a change in Shapley values, which are a measure of how important a feature is to the model's output. If the importance order changes, that suggests that something is changing in the model. So those are things that have been looked at. Then you need to verify that the system is correctly configured and there hasn't been a configuration error made, and then test the accuracy of the output, which, because of the issue with external proficiency testing and models potentially being different, is generally parallel screening with a second method. And so the example here is a neural network model for flow cytometry for minimal residual disease detection in CLL. And essentially, they're trying to detect a clonal population if it exists. This was done at Mayo by Jansen Seeholt and published this year. So their monitoring strategy had all three components. For the input data, they had, I thought, a really creative approach where they did principal components analysis, which is essentially a data compression down, and it takes multiple features and sort of strips out features that aren't varying very much or are correlated, and leaves sort of a combination of features that have most of the variation in the data set. You can take that and then you can regenerate the original data set from it, but the regeneration isn't perfect. There is an error in that regeneration, like in expanding a JPEG, for example, because you lose some data when you do that initial compression. And so you're expanding back to something a little different. You can measure that difference. So they're basically looking at Euclidean distance calculation to measure the difference between the reconstructed data and the original data. And they did that for their original training data. And each sample, they do that to compare it to the original training data. And if the difference between the expanded data, if the difference between the expanded data and the original data for that sample is substantially different from their original data, it suggests that there might be a difference in relationships between the data elements. And so not only, this doesn't look just at the distribution of a single data element, it sort of looks at the relationships between the data elements too, which is one reason why I thought it was a really creative approach. So if 5 samples are out by 3SD, in the difference between, too many differences here, but if the original to reconstructed difference is out more than 3 standard deviations, and that happens 5 times in a day, that's a flag to investigate for drift or shift. They test system integrity by processing a prepared data file, the same data file every day, through the pipeline, checking the data file at each point and making sure it's the same. So that'll identify if something has changed about the system. And finally, they check the accuracy of the output by looking at the frequency of, for positives, the frequency of discordance between the model output and the final interpretation, because they review all the positives. And then there's a random sampling of the negatives, 14 cases per month, and they allow no more than 1 false negative per 6 months. And so that gives them all 3. They check the input data, the system integrity, and the accuracy of the output. Okay, so some additional considerations, just things to think about. The initial performance claims verification is usually on retrospective data because sometimes you need to know outcomes, and you typically have a lot of retrospective data. If there's subgroup bias possible, you need to confirm the accuracy in the relevant subgroups, and that using appropriate numbers. And so that means that you may need to get, a complete study of just a particular subgroup of patients to make sure that you're not, your inaccuracy isn't greater in that subgroup. So that may require several studies. Doing a prospective performance evaluation is good practice, using a realistic case mix and running it in the background or in parallel to confirm the performance before you go live with it. And then ultimately bringing the tool live and monitoring the data and performance over time. All right. So to wrap up, key points from all of this. We covered a lot of material. Machine learning is going to enable exciting new tools. I think there's no question about that. It's going to be used widely. The systems implemented in the lab that contribute to patient results, we probably should, by default, treat them as if they are covered by CLIA. Guidelines and regulations for managing the systems are immature and they're in development. We're hoping to see that develop fairly rapidly over the next year or 2. In the meantime, there are reasonable analogies you can make between traditional CLIA requirements and some of the needs for ML system validation. Good performance from machine learning systems isn't guaranteed just because they're machine learning and cool. You have to carefully select and implement them correctly, and then verify their performance, and then continue to verify their performance over time, just like any laboratory test. There are new metrics and analyses to become familiar with, but there are examples of good practices in deployment becoming available, and we can use those as models. And we expect that those to be aggregated into best practices. So thank you. Hopefully you'll find that useful.
Thank you very much, Dr. Harrison. So we don't have a lot of time, but maybe for 2 quick questions for Dr. Harrison, please. Yes.
Hello. I just had, I guess the question is twofold. If you've heard at the regulatory level any sort of discussions about specific guidelines for cybersecurity, just because maybe I guess that's part of it, is like maybe I'm a paranoid person, but I'm just wondering, if there was a virus or something where, there's a little bit of adversarial noise that gets introduced, is that something with like the daily performance monitoring that could be found and addressed in like a quick fashion, I guess?
Yes. Sorry. people who like to think about worst case scenarios have suggested that as a possibility. I don't know anybody that's doing any real work on it yet. And I don't know that we don't have a defined scenario where someone from the outside could do that. But there is a possibility. Now, what you're really talking about is somebody changing a whole slide image from the outside such that it has adversarial noise in it that is selected to target a particular model, because that adversarial noise is for that particular model. It wouldn't have the same effect on another model. And so there are issues there that would make it somewhat challenging for somebody to do that. I think one of the things to think about is that the fact that you can do that shows you that there are patterns in the data that the model doesn't have covered. And we don't know how many of those there are, and whether models, whether some other change would just happen to run across them. If they're really rare, then it's probably very unlikely that you would, by default, or that you would just somehow generate one. But if they're not that rare, then you might. And we need more experience with these models to understand what that situation is. There are other security issues too, and things like, is the model implemented locally, or is it implemented on a huge cloud somewhere, and what sort of communications go on and how those are secured and so forth. And then there are other concerns about training the models, which most individual healthcare systems, unless they're building their own model, wouldn't be an issue. But in training a model, is there any patient identifying data in there that would allow somebody to find out from the model information that they shouldn't?
So 2 more questions. I just want to mention very quickly, Jim, I'm really happy that, to see that you cover in so much detail the machine learning, because that has direct ability for histopathology. So out of all the
there is a high potential for arm waving in the domain. And so it's, detail is necessary to some extent.
Dr. Adi?
Yeah. It's a very nice presentation. I learned a lot about mathematics and, very nice. Now, you said something about external proficiency testing, and looks like that is not going to be the pattern whereby, when we go to CLEAR and CAP, doesn't look like external proficiency testing is going to be the way to go. And so, but there's just so much that is still not known about AI in pathology. However, right, for practical reasons or purposes, a lot of labs are more likely and are probably moving towards adopting the AI algorithms that are helpful in screening rather than in being predictive, whether in binary or multinodal. So example would be like trying to AI for KI67, where it screens for me, or AI looking for nodal deposits of cancer. So I'm not relying on the AI to tell me whether there's deposit or not, but I'm using the AI to screen as a pathologist what areas I need to pay attention to. So I think ultimately there are going to be different levels of validation guidelines with time. Now, of course, we don't really know.
Yeah, so people are talking about risk-based regulatory frameworks, where you've got the acuity, or rather the impact of the decision and the impact of an error and the likelihood of an error. And as the impact goes up and as the likelihood goes up, you have more stringent regulations. So that's, the FDA probably would implement things along those lines. Of course, the way the FDA and CMS are going to interact hasn't been defined. And CMS is, administers CLIA, and the FDA administers this stuff about, can you sell it? And so that still needs to be worked out. So now talking about proficiency testing, there is the potential that you could do something like once the images are digital, a site could send a proficiency test authority 100 sample images from their site. those images could be used to generate a signature for their histology lab, which could then be overlaid on a test image and generate an image that has characteristics similar to the site. And that could then be used for proficiency testing. It's theoretically possible to do that, but I don't know if that's the way things will ultimately go. And then the other possibility, of course, is to really figure out the normalization in software, and then get every site to normalize in the same way. And then, you know, sites could transfer those images.
Okay. So it's time to adjourn. Please join us for the reception.